Am I audible? Am I audible, Saurabh?
Yeah, you are audible,
Yeah.
sir.
Thank you. Thank you very much. So good afternoon, everyone. I, Professor Abhishek Kumar Singh, coordinator of the event with Professor Saurabh Srivastava. Welcome you all. Actually, Director IITISM, Professor Rajiv Shekhar, was to inaugurate the session, but due to his health problem, he couldn't make it. So we are actually having with us Professor Chiranjeev Kumar, Dean Academic, HOD Maths and Computing, Professor R.K. Upadhyay, Sri Sushim Srivastava, Senior Director, Qualcomm India, Mr. Souvik Basu, Staff Program Manager, Qualcomm India, faculty members, students, ladies and gentlemen. So I welcome you all again. As we are all set to for a joint webinar with Qualcomm entitled Emerging Trends in Fundamental System Research. We know all that Qualcomm is an industry leader in integrated circuit design. They have been instrumental in bringing a technology revolution with products like the Snapdragon processor, which powers millions of mobile devices today. This webinar consisting of 5 talks scheduled bi-weekly starting from today and will be beneficial for students from computer science, mathematics and computing, electronics and electrical engineering. The first talk will have no prerequisite and will be open to all. The subsequent talk will become more engrossing towards concepts involving in building complex fundamental system. The first talk in the series will be entitled as Enabling the Rise of a Smartphone, which will be delivered by Mr. Souvik Basu, Staff Program Manager, Qualcomm India. Now, let me introduce Sri Sushim Srivastava, Senior Director, Qualcomm India. Actually, Sri Sushim started his career as a 3G protocol stack engineer and moved forward and took different roles like chipset software lead. He then continued to work on 4G and 5G connectivity, multimedia and application processor software. He has been working in the wireless semiconductor industry for almost 22 years from now. The past 5 years of which he has spent working on compilers, cloud computing, machine learning, and software security. He has been and hope to remain passionate about computer science ecosystem on a global scale. I will now request him to speak few words. Sri Sushim Srivastava, please.
First of all, I'm very happy to be here at IIT Dhanbad and speaking on a variety of topics. So this talk series, what we are trying to do is, generally we had presentations at very deep dive levels, which are more researchy. So we prepared a series where a BTech second year onwards, they can appreciate computer systems engineering. So first one opens up with a very, history of smartphone. Then we go a deep dive into how compilers are enabling the end products. And then slowly what happens is the deep dive optimization, which we used to present to PhD or graduate students. What we have done is we have brought them to a simple level to explain it to a second year BTech graduate from any of the circuit branches. So this is how this whole talk series is, because we have already also spoken earlier at different institutes to graduate students and to PhD candidates, but we wanted to reach computer systems to a wider domain. And since computer systems is core of computer science engineering or circuital branches, it involves a lot of mathematics, and there is a problem in connecting these to end product, how end product is, you can see this. So we specifically worked on these 5 lectures so that we are able to connect computer systems engineering to end product. For example, the last talk will talk about a domain specific language. That domain specific language halide, when we are explaining it, we are not talking about systems engineering, but the language. So anybody working on image processing, halide is image processing language. So they can join that talk and they can use it for image processing. So this talk will run through, series will run through altogether from the mobile smartphone history to image processing and some concept like how systems engineering is enabling machine learning and all those things will also be covered. Again, very thankful to IIT Dhanbad to giving us this opportunity to talk to one of the best talents in India. And we are very happy to be speaking here.
Yeah, thank you, Shri Shushim Srivastaji. Now, I will request Professor Saurabh to take the coordination of this inaugural session, and please start the talk of Mr. Souvik.
Thank you, sir. Thank you, Sushim. So this was the beginning of probably a very long collaboration between IITISM and Qualcomm. And as sir and Sushim has already pointed out, the main idea is to actually get that amount of knowledge, whichever can be presented to a typical BTech second year student in a form that is easily absorbable, right? This is the overall idea of this whole webinar. And as Sushim has already pointed out, that we'll start off with extremely basic stuff, something that that doesn't have any prerequisites whatsoever, and over a period of time we'll graduate to more complex stuff, more cutting edge stuff, right? So in this series we are going to start off today's talk with Souvik being our speaker. Souvik, you can now try and share your screen. I mean, I just held him back from sharing his screen. I'm really sorry for that. So now Souvik can you can also get into the picture, and let me just speak a few words about Souvik as he prepares himself for the talk. So Souvik has been associated with the VLSI industry for about 2 decades now. Over the years, he has worked in different technical as well as managerial roles. He has developed EDA and CAD methodologies in FE and PD domains as part of a large consumer and server class technology developments. Not only has he played a significant role towards internal product R&D, he has also taken up customer-facing roles as part of his responsibilities. And Souvik, well, he holds an MTech degree from IIT Kanpur, an executive business management degree from IIM Kolkata, and a master's degrees in business laws from NLSUI Bangalore. So you can understand the kind of skill set he has, right? Such a varied skill set. It's not that easy to find. So Souvik, I won't really waste much of a time. We have probably killed up a lot of time already, which was supposed to be given to you. So from here onwards, I'm just going to hand over the podium to Souvik. Souvik, you can start.
Okay, sure. Thank you, Professor Saurabh, and also thank you, Professor Abhishek, for all the introduction. And Shushim also, thanks for the introduction of the overall session that we are planning. Let us get started. Welcome, IIT Dhanbad team, the students and the faculty members. As part of this series that we are planning for total 5 presentations, so today we'll start with the beginning topic, which will be quite interesting, I believe, to understand that how Qualcomm, being a company, we have done the development of smartphone starting from 1983 onwards, when Qualcomm was founded, and then taken it to the multiple stages of G transitions, like the 1G, 2G, 3G, 4G, 5G. And also in that process, how we can integrate many features beyond mobile modems and the mobile communication, like different multimedia features, audio, video, graphics, and many other features currently with the artificial intelligence and all of these. So we'll cover all these areas as part of the overall presentation, which is titled as Enabling the Rise of the Smartphone, Chronicles of the Development History at Qualcomm. And we will touch upon multiple verticals or the business domains where we operate, and also the emerging domains like some of the adjacent markets, automotive and all that. Okay, so let us continue. Let me put it in the slide mode and continue. Okay. I hope these slides are visible and it is transitioning properly. So to start with, we will see one of the fundamental device that is there with most of us, or maybe I can tell that all of us, that is a smartphone. And this is really a revolutionizing technology which has evolved in last 30 years. And we will see that what is the journey and how we have developed it, and what are the key technologies, starting from the hardware as well as some of the software side of the technologies, and many other research areas that we have incorporated in as part of this set of mobile smartphone devices. And it is not only actually smartphone, but there are many other mobile devices we are also talking about nowadays. It can be a mobile communication devices, or the mobile IoT devices, or the vehicles, so many of them. So, but the smartphone is key, and the smartphone technologies that are developed, and the smartphone roadmap that we have, or the wireless roadmap that we have, those are enabling across the board multiple developments, and some of the cutting edge products and some of the differentiating products. We will come to the differentiating aspects, like some of the low power technologies, which is quite key, and that is differentiating Qualcomm from other competitors. I mean, obviously, the other technologies are also important, like the 1G, 2G, 3G that we developed over the period of time. And then the fine tuning of that, and the patent portfolios that we have surrounding it, and the key enablers like this low power is one of them, and then we also have the new domains where we are utilizing the machine learning, artificial intelligence, all these areas significantly. Now, coming to the specifics in this slide, right? So what we are seeing is that it is a truly democratizing device. Okay, we have billions of smartphones today, and it is continuously growing. And there is a cycle of upgrade also we are seeing, like 3G to 4G, 4G to 5G in the coming days. So all of that. And it is driven by many things, like we have the high quality multimedia with the music playback, immersing sound, and now the 8K Ultra HD videos, HD gaming console, and multi-sensor digital cameras and multi-camera systems, including the front and back side cameras. Then the geo-positioning, which is the location-based navigation, and continuous evolution of that, including multiple international and national standards that we are supporting. On the speed side, it is increasing. It is many multi gigabits, even coming up to 100 gigabits as part of the 5G standards. And we will see as part of this presentation that how we focused on the data part of it, starting from the 3G era, and continue with the 4G, and it has tremendously improved at the era of 5G, which we are transitioning now, and internet connectivity. And then this quite key thing is the long battery life. And along with the long battery life, what we have today is that fast charging. So basically, it takes significantly less time today to charge with the new technologies that we have. We can charge it in 15 minutes or even half an hour. Quite powerful batteries which can last for a day or so. And there are multiple days lasting low power devices also we have, which are active in terms of its this content usage, content viewing, content creation, and as well as a mobile device. And it is expanding to additional domains, like we have the always on, always connected PC and the laptops. That is again another game changer which we are driving. Okay, so we'll see the journey in next close to 1 hour, and let us continue. So we will start with first the mobile part, like the 1G, 2G, all these technologies, 3G, 4G, and then we'll take it to the other components of the Snapdragon processor, like this multimedia, graphics, CPU, GPU, then NPU also is another part which is used for artificial intelligence, and key other enablers. Okay, so to get started, if we look back in 1983, it is the introduction of the first generation, that is we call 1G wireless this communication, which is called as analog AMPS. Okay, and this is the era. And before we get started, we'll also see that how what is the general duration of our G transition. Okay, so if you think that around 1980s we started with 1G, then we will see that around 1990s we are starting with 2G, and around 2000 we are starting with 3G, 2010 we are starting with the 4G, and around 2020 we are starting with 5G. Okay, so that means these are the G transitions are happening around every 10 years. And we'll come to that G transition and the specifications and all that things down the line. So in 1983, it was analog based initial processing, where we see that the overall it was distributed in terms of hexagon type of a cells. And in reality, this is a kind of a modeling kind of thing we can think of, which is a hexagon, but essentially it is like a circle where the overlaps are there. But yeah, if you consider this a hexagon and consider the technology that was there as part of this AMPS, there we see that this frequency reuse is limited. Okay, and there are channels of the 30 kilohertz which are again separated, and they are we cannot reuse those frequencies for the neighboring cells. So that means the channel capacity goes down if we can't reuse the capacity of this each channel bandwidth, and that means a limited number of concurrent users will be able to support. Anyway, I think we still would like to recognize that this is a system which was developed and it was getting used. The phones were a little big and bulky, and still it is a usable system through which we entered in the era of mobility. And if you really want to see the long history of wireless, then if you want to see the history of, say, maybe there is a history even close to 100 years, where many things were developed periodically, but those were not as sophisticated as it was in 1983 as part of the first generation AMPS system. But there is still a long history and R&D with Nikola Tesla, and others. We had Indian inventors, all of them. Okay, so so there were a couple of other limitations, and not only the spectrum, but also it was suffering from the interference and the noise issues. And analog was that way looking like not scalable. And that means we cannot, we were not having sufficient bandwidth to be shared across these cells. And there was a motivation in the industry to explore the digital method of communication, which will enable more channel capacity as well as better noise handling, error handling, and all that. So that was the motivation to go to digital. I think we'll quickly go because there are multiple other slides. So let us go to the digital. So it was the late 80s and the early 90s. So around we can think of like 8 to 10 years duration, when we landed in the domain of 2G digital cellular wireless. Okay, so 2G digital cellular, that was a time when digital wireless system was getting kind of getting redefined, and the new discoveries were happening. So as we see here, we have the previously FDMA, that is a frequency division multiple access, which was there, which was giving only one user per radio channel. And the first thought that many of the industry teams, they thought that the easy way to do will be to do it at TDMA, that is a time division multiple access. And this is a simple representation of the TDMA, where there are 3 time slots and 3 users were sharing the time slot, and it was increasing the capacity by 3x. Okay, so this was the fundamental thought process when the industry wanted to move from FDMA to TDMA. But what Qualcomm did was Qualcomm went beyond this. And Qualcomm thought and also conceptualized, and even we'll see how Qualcomm created the whole set of end-to-end infrastructure to go beyond this 3x capacity and to move it to a 10 to 20x capacity through the spectrum technology, and that technology was named as a code division multiple access, or the CDMA. So in this case, what happened was it was a fundamental research we will see in the next slides. So Qualcomm contributed in this fundamental research, and then Qualcomm demonstrated it starting from scratch, starting from SoC design to the system design to the whole baseband and the transmission system design, and enabled it end to end to prove that it is superior and it works quite well, and there is no call drop, there is not much interference, and many other channel related, wireless channel related limitations, or the channel modeling. If we see, we have many other interference, multipath propagation, fading, and all these things. So we worked on all of those areas to see that they are addressed significantly, and we are getting a very high capacity as part of the 2G wireless. So I think we'll see further in the next slides. So essentially, it was a better digital alternative to TDMA, and capacity is important because it also translates to cost. So why this cost? So cost means if we give a technology, and this is true at that point in 1980s, 1990s, and even today, as that is once we give a technology to our client, whoever it is, the service providers and all, or any other tech company who is developing a technology in any of the domains like automotive, etc. So we need to give them a superior technology with a very competitive price, and give them a value proposition that if they go to a technology, because there may be some technology, but then they need to go to the next one. So in that process, what is the value proposition? So in the case of a 2G CDMA, the value proposition was that within the same cost of the infrastructure, they are getting higher capacity, and that higher capacity, I mean, you see, it is a significant high capacity at that point of time, and they were in a position to monetize it, like in terms of the user base. And that is the method that Qualcomm has continued. Like there is a business value proposition, there is a technology development, there are fundamental research, there are patents and intellectual property, and also working with the ecosystem to see that the industry is growing, and finally it is creating a very democratized ecosystem where everybody is having a phone or a smartphone. So the next slide. So this is our fundamental work that was done by Klein Gilhausen, who is one of the founding members of Qualcomm. So Qualcomm had around 7 founding members, including there were very prominent researchers and these university professors who were part of Qualcomm Foundation team. And this is the memo which further got published. This is the seminal memo which was the fundamental research that Qualcomm did, and Klein was spearheading this. So the calculations were quite complex. I think today we are not going into the calculations, but if somebody is going into this wireless domain, we'll see that how the details are done and what are the methods of these different calculations, and frequency domain to the analysis, and then the code division, multiplexing, and the different this spectrum technologies, how the code is getting embedded, and then the spectrum, how it helps in terms of overcoming the noisy environments, and then how it is going in the channel, and then how it is I mean, today it is also packetized, and then finally how this the receiver works in terms of overcoming this noise limit and understanding the communication that is coming as part of the individual CDMA packets. So anyway, it was a path-breaking thing at that point of time, and the theoretical capacity gain for CDMA over FDMA was very staggering, and we continued. And as you see, this is 1988, so this is around say a couple of close to 10 years from the 1G. By the way, any G transition, when we tell it is 1G, 2G, 3G, so there are different intermediate small incremental improvement that happens, and then it gets all added up to create the next generation. Like today we have 5G, which is we will see later it is 3GPP release 18 or so, and 16, 17, 18. Or 14 onwards it started, and now the work is going on for 6G. So we always continuously innovate, and we always continuously publish internally and externally. And this is one of the example where we invented CDMA with very high data capacity at that point of time. This is a slide which is trying to explain that how CDMA works. So, so there are, we can say that what we can say is that it is like a partition system, and every user is having their code, kind of a unique code. And whatever the communication is happening, that communication is spread and encoded with the particular user's code. And initially it is at a specific bandwidth, but it is spread with a particular code. And this, once we look at in a real system, it will look different for different users with different codes. And then it gets transmitted, and then it is reconstructed at the user side, overcoming the noise limit. So that means the other signals which are like this are the spread one. So that is the representation of the noise. But on the receiver side, we are reconstructing the actual signal using the inverse of the code being applied. You can think it that way. And also, Qualcomm looked into the statistical modeling of this communication, like how frequently generally people talk through, and like there is a pause interval in most of the communication, and that particular number is shown here. And those were also factored in to improve the utilization of the channel. Okay, let us go to the next one because we have to cover a few other things. So what we see is that once Qualcomm invented CDMA, that time there was other parts of the industry who were working on TDMA. And TDMA was very straightforward, but not CDMA. CDMA had the fundamental breakthrough, and the approach itself is quite unique. So many people they could not understand what CDMA is trying to do, or what how it can be further scaled up. So there were quite a lot of skepticism at this point of time in industry around that 1980s end or 1990s beginning. Even some of them, they told it is too late, already TDMA is going on, and some told that it won't work because in the real world it will not happen, or it was too complex, or even some professors told that it is violating the law of physics. So that was the comments at that point of time. And but Qualcomm, being the inventor, and we had a very strong IP mindset, and also we understood that it is a quite important market which will help not only from the business point of view, but also overall the way we are seeing the information is available now at any point of time. So we envisioned that this is required to be driven, and Qualcomm was committed to build the entire system end to end to prove that the CDMA is working. And that way, we entered into the chips and the phones and the base station, all the three, to ensure that we have the capability and not only proof of concept, but actually the running and working system, which proves that this technology is first of all, it is working, and second thing is that there is a further future, which we will see that how we scale it from 3G to 4G and all. So it was actually a 2G, and then we scaled to 3G in the similar lines. Okay, so I think these are some of the challenges this base station and this user equipment (UE) we call. So these are sometimes we see the near far power challenge. So that was there from beginning, and that required a certain power modulation from the antenna side to see that there is a fair amount of power distribution, and the phones which are near to the base station, or they are receiving the little less amount of antenna power, and those are judged on the go, and then the ones which are at a further distance, for them the power requirement is high, so that was considered. And then also the part is a cell edge challenge, that is basically a user who is mobile, and he is transitioning from one cell to other, and there used to be a call drop. And the technologies were developed to minimize this call drop, and that is called the soft handoff. And the soft handoff was enabled through this multiple ways of calculations to understand that how and when the user is switching from one cell to other cell. Multi-part fading and the other channel related things, as we talked about, there are other interferences and all, which were modeled, and technologies were developed to see that these we understand that what are the channel structure once the user is there, and it works even outside of the house or even inside of the house, and based on the kind of this channel model and actual the physical orientation of the different items, we can do a good job in terms of seeing that the antennas are propagating in a right manner, so that we are getting the optimal bandwidth throughput, and the call drop is minimized. And these technologies further enhanced, and we have entered in the era of MIMO, where even we have multiple antennas and multiple, say, custom beamforming techniques through which we can see that the right areas gets the focus, and wherever we don't need the antenna to propagate, we optimize the power of these transmitting antennas, and essentially ensuring that the low power quality is maintained. Okay, going to the next slide. So we developed this technology, and over the period of time, we wanted to get it proven through our ecosystem partners. So Qualcomm operates with their ecosystem partners quite closely, and at the initial time when we were transitioning from that TDMA to CDMA, there were limited number of partners, and as we told that the TDMA, there were some partners who were in the TDMA path. So it was looking little difficult to get the right partner for the CDMA technology for the demonstration, because you note that these are the service providers, and Qualcomm entered in the market of cheap base station and this overall platform, but the service providing is a different ball game, because it's the other geographic span and all that comes in. So we had to partner with the service provider, and we partnered with Pacific Telesis in Los Angeles, Pactel, at that point of time, and worked towards the proof of concept and the subsequent rollout in the market of this 3GMA technology. There was a very successful demo. There are a lot of details of that demo. We'll not go into that, but that demo, these are the pictures we see. It was a mobile van with the antennas, and then people, even some of them are still with Qualcomm. One of them is our CTO. And we had a very successful demo of this CDMA technology, which ensured that we are in the right direction as part of the CDMA propagation in the market. Okay, so we also received the IEEE Milestone Award for this demo in future, not immediately, but it was recognized as a milestone event. And IEEE milestone events are very, very, say, prestigious, and it is very rare. It is not, it doesn't happen so frequently. So this milestone award was such a prestigious, and it was such a recognition, and Qualcomm received it because of this CDMA introduction. And there are many more milestones. We'll come to that, but this is a very significant one. So we continued with the CDMA. There are many testings. We'll not go into those details, but Qualcomm team, including Qualcomm engineers, they went into field and did the system testing, and there were mostly it was Qualcomm equipments, and CDMA at that time only was with Qualcomm. So and then slowly the other vendors also picked it up, and we made it as part of the standard as well. And once other vendors picked it up, we also enabled interoperability through the standards. And those are all part of the historical development in the CDMA technology. So next is the how and what are the other factors that helped us. So one of the factor was that if you look at wireless communication and the corresponding algorithms, and we will see that from all the G transitions, we had to go to better and better algorithms. And to enable better and better algorithms, actually, we had to go for more processing power. And the better algorithms were actually giving us better this say the power data rate, as well as many other features that we were looking for. Now the requirement was to include a lot of transistors to support this high-end algorithms. And to do that, we used, or maybe we were good to use the transistor count, the Moore's law, what generally we call it, that is having approximately double the this transistors per square inch every 18 months or every 2 years. And that Moore's law helped us, or we also call it, there are other terminologies as well. But anyway, we used all these features and created a superior and superior technologies, like we moved from 2G to 3G, 3G to 4G, and it continued. And all these were done with the other factors like power, performance, area, all of them in mind. So now this is another demonstration how we moved in the technology node, and starting with the Qualcomm Alpha 2 phone and with the 1.2 micron process, to the beta phone with the 0.8 micron process, and then QCP 300 phone, which is also based on MSM2. Actually, we started with MSM1, we'll come to that, but MSM2 was powering this Qualcomm QCP 800 phone in the 0.8 micron process, that is 500 nanometer. Okay. And form factor got reduced, and then we also strive to standardize this CDMA technology as part of once we understood that we are in the right path, that we can improve our phones in terms of our the size and all, and the CDMA also can mature, and then we pushed to make CDMA as a standard. So CDMA was standardized by TIA / EIA. This is a standardization body, which is called as IS 95A in July 1993. And there are many different milestones. I will not go into all the details, but this standardization was quite important in terms of the Qualcomm's dominance in the smartphone domain, as well as building an ecosystem and the industry around it. And we'll see how it continued in the future time. So as we mentioned, we did a jump start in the CDMA industry, and the industry was totally built by Qualcomm at the early stage, and we were doing that time the chips and also the phones, as well as the equipments. And we had partnerships as well, like in the phone we had partnership with the Sony from 1994. Similarly, partnership with Nortel on the infrastructure development, and then we continued with those businesses for some more time to ensure that the CDMA industry is coming up properly. There is no scarcity of the this development resources, and we can roll it out to the users. And once we were successful, then we thought that it is good for the industry to take up certain capabilities, like phone business was sold to Kyocera, then this infrastructure was sold to Ericsson. But that did not reduce the capability of Qualcomm, because Qualcomm was still, and today also Qualcomm is still capable of building own phones and own infrastructure equipments. But we wanted to focus on the IPs and this SoC and the chipset design. Chipset is basically SoC and other components. And what we can tell is that the whole heart of these phones and even some of the infrastructures, the core of it is inside developed by Qualcomm. And there are in the ecosystem, there are democratic way where all the partners are building their phones, and they're also bringing their innovations. And we see that large set of handset providers, starting with the major US providers as well as the Chinese providers like Oppo, Vivo, Xiaomi, all of them, like the Android premium segment. So all these things, we see that quite dominance of Qualcomm chipsets, and especially in the high tier era, high tier sections. I'll come to some of the performance modeling at later point of time, and the similar infrastructure also we have long story. We'll not go into that, but in 5G we are also going to see that the infrastructure is rightly done and it is optimized in terms of performance, power, and all of that. So coming to the other type of scaling that we noticed in that 7-8 years period, as we see that we started in 1993 around 1,300 employees, and we went more than 11,000 employees in 1999. So that was a very interesting era when we developed 2G and then moved to 3G. So we'll start the next section on the 3G. So 3G also was developed on the similar paradigm that we wanted to make better use of these 2G technologies that we have developed. That is the fundamental CDMA, and then we wanted to understand what are the next requirements, because the users were having a very good voice communication with the 2G. And at least they had a mobility, they could able to call to any wider location as long as this antenna support and the coverage was there. And but still it was a bit costly because the capacity was still lower compared to as of today. But then we try to understand that what best further we can do, because is voice is the only thing, or we need anything beyond it. So as part of that, what we understood is that the data is the quite next important thing, because we had the capacity for voice, and we wanted to increase the capacity, and we wanted to see that if a voice communication is happening perfectly and at least quite good enough at that state of the art, then if we have additional bandwidth, then how do we use it? That was the question, and then the data part fit in that additional bandwidth that we could able to drive as part of our processors and the smartphones. So then once we decided that it is data, then we had to decide that what is the format of it, like which way we want to communicate. So that was the era when the TCP/IP and in the fixed LAN it was available. And we thought that it is better to follow the standard of TCP/IP and then push it the same way, the packet structure. And only thing is that it will be IP stack, but in between there will be wireless. Like there will be wireless base station, and it will go through the internet in certain cases, and users will not be tied with wired communication with a wired LAN was giving the users the feature at home. So net it was drive towards data and drive towards standardization and the packet-based application. So that way we had to merge the technology of CDMA with the TCP/IP protocol, and we'll see that how we did it. So this is a slide which is covering the early this packetization of the data and the early data network that is we call it a EVDO. Okay. In the this CDMA 2000 got evolved at that point of time. So you may remember the other one was IS95A, and then it got evolved into CDMA 2000, where the voice packets were there, and then along with that, the additional bandwidth, we created this standard called EVDO, which will become the packet-based transmission as part of a 3G, and that also got enabled as part of a overall mobile phone-based communication. The data rate was lower, but it was a very good starting point for the next generation data based this communication, and we'll see the evolution of that as well. So this EVDO, it was also it was earlier called a high data rate, but it was called that evolution data optimized EVDO based on the standardization. And again, we worked with the standards body to see that it is also a kind of a democratized standard, so that others can pick it up and we can create a industry and industry ecosystem based on this standardization. Okay, and this went into 4G and 5G. Okay, I think EVDO also was another milestone. I was talking about some of the milestones. So EVDO also was another recognized milestone, which was the beginning of a data transition as part of the 3G. Okay, so I'll not go into details, but there are patents, and as you see, all these details are there. But net, it was a very big, important change, which enabled the data transition. Okay. So how it was accepted in the market? It was accepted very positively, and as we see that one of the first Amazon Kindle, they enabled EVDO for internet connectivity. So we had interactions with the people like all the CEOs of these internet companies, and they also understood that what additional they can do, like internet and the mobile internet especially, it was becoming a big shift, and people thought of even starting with the Amazon Kindle, that how they can move from a product-based economy to a service-based economy. So that is where we started the concept of a service, and whatever the service-based economies that we see, that become popular because of the reach and the scalability that wireless could provide. And we created a industry segment that way in itself, which further got expanded once we improved the bandwidth, and it also went into the wireline and wireless categories together. Data technologies. So this within 3G, so we created many enhanced data communication. So as we mentioned, right, the technologies, though we call 3G, 4G, they are span across 10 years, but there are incremental improvements that happens within that time span. So like within 3G, this is an example that how the data rate got evolved. So the starting with the 3G, with the EVDO and all, we had a certain data rate which went from Rev A to Rev B, and we went up to 14.7 Mbps. But then with the mobile 3G, with the WCDMA and HSPA, those are again other standards. Those timelines are mentioned. So we went from 14.4 megabits to 63 plus megabits per second, and these are called the HSPA and the HSPA plus. So you see that what is such a big jump, like where we were even not 1 megabits per second in 2G, there in 3G in the first stage, we went up to 14.7 Mbps. And in the second phase or the later phase, we went up to 63 or 64 Mbps. And that further continued, and this is still within 3G. And you may recall, not only in India but worldwide, we had a data revolution with 3G, and that continued for 4G as well. And HSPA is called the high-speed packet access, and these are the timelines for different HSPA standard evolution, and the timeline like 2002, 2004, 2007 onwards, and millions of connections. Like 2007, the EVDO passed 50 million connections, and this is Q1 2008, that is the HSPA crossed 50 million. June 2008, it was first HSPA plus. It went up to 21 Mbps, and then 2010 September, we had DC HSPA plus commercial launch. This is other chart, the previous one that we saw, that how we went from HSPA to the next one, that is this LTE and the LTE Advanced. So this LTE and the LTE Advanced, as we see that the data rate, like it in 2010, 100 Mbps, and then significantly it went up with the Snapdragon X5 and X7 and X10, X12, all these LTE modems with 150 Mbps to 300, 450, and 600 Mbps bandwidth. And the duration, as we see, and then we reached 1 gigabit per second in as part of the X16 LTE modem, and that happened itself a couple of years back, around 5 years back. And today we are reaching up to 100 gigabit per second as well. So overall, we are getting to see a faster and better mobile broadband with these advancements. And these advancements happened because of the very breakthrough and the fundamental research that Qualcomm did, as well as the product development expertise with the hundreds of products that and these technologies that we have developed over the period of time. And this excellence is is visible as part of our achievements and the worldwide team's execution and the research capabilities. Going to the next part, so we'll just, I think we'll accelerate it, otherwise there are many other things. So as part of this 4G LTE, which is also moving towards the 5G, that was the way we transitioned to 5G. So we added many features which were covered in our research and our patents and all. Like this one is the carrier aggregation, coordinated this multiple processing, then low power DTX, different handoff mechanisms, then LTE broadband, hybrid air queues, and we had the small cell related technologies, and also there are fundamental this coding related research on OFDMA, and we also worked on this SCFDMA and a few other things. And then other important things become the automotive, where it is not only the low speed, but it is the C2VX, we call, like the individual to vehicle to anything, like the vehicle to vehicle communication, vehicle to user communication, all of them, those were possible. And those are now going into the next generation cars as part of our automotive market. Also, there are many MIMO techniques and all these things were developed. And the capacity in the next stage in 5G, it goes I mean, significant improvements, like the numbers are that this way, that in terms of latency, there is a 10x decrease in the latency. In terms of the spectrum efficiency, it is 3 times more efficient from 4G to 5G. Network efficiency is 100 times. Then 10 times is the experience throughput. Traffic capacity is high. Connection density also is quite high. And this connection density is another thing. I mean, all these things are based on looking the future requirements and even some of the limitations that 4G was facing. Like in a dense environment, maybe like a stadium or something, we were seeing that there may be a possibility of call drop. So 5G introduced the need for this density support, and we enabled it as part of a 5G rollout. There are many other things, like as I mentioned, this 3GPP release 16, 17, 18, or starting with 14, up to 13 was a 4G. And then every release is improving the capabilities. I'll not go into all the details, but release 18 is also now available. So for 15, 16, 17, 18, all of them enriched 5G. And we are supporting all the 5G requirements as part of our modem and as part of our overall end-to-end capabilities. Now let us look at the intellectual property part, that is which is measured in terms of patents. And along with patents, we can have other measures of intellectual properties, like it can be other measures which are there, but we will focus on patents. And on the patent side, we will focus on the measurements that are done by the independent bodies. And this is a graph which is done by IP Watchdog, which is an independent body. And what it does is that it is showing it in terms of patent count as well as the patent value and the impact. So, and what is more important is the patent value and the impact, because that gives the protection, that gives the edge in the overall competitiveness, and we actually evaluate based on the overall value that it brings up, right, over the period of time. So if we just go by the raw numbers, then also Qualcomm is quite ahead of many of the competitors, and continuously we are doing many thousands of patents per year. But if we look at it in terms of the impact, and there are certain impact scores are there, which is developed by our third party. So that way, Qualcomm, as you see, this blue line is Qualcomm, and we are very significantly ahead of our competitors, and that is how we are maintaining our leadership in research, development, and product rollout, and reach out to the customers, and acceptance by the worldwide customer base that we have. Okay, let us look into a few other things, like how we are enabling the whole ecosystem, including the software side as well. So this hardware part, and especially the wireless communication and the 4G and the 5G, they are enabling anybody and everybody to use these fundamental computing capabilities. And we'll see that we have CPU, is there are multiple CPUs actually. Then we have the graphics processing unit. We have this vector processing, also called this NPU or the DSPs. We call it Qualcomm hexagon DSPs. So those are there. So many types of processing, they are working together and in an optimized way, so that this set of software works in the best possible way in the handheld devices, as well as I mentioned, we also have our set of laptop and all those kind of devices. In summary, we are, I think it is more than $1 trillion of software economy is based on the computing power that the hardware is supporting. And Qualcomm is one of the leader in the mobile domain in terms of supporting the hardware and the technologies and all the new advances that we'll see in the later part. I think we did not talk about the sensors. So sensors are again a bigger area through which we interface with the physical world. Okay, so this is a graphic way of representing that what all things we have integrated over the period of time and how we have transitioned from the tech node to tech node. This is there are 13 process nodes we have transitioned from MSM1 to this current one of the latest one called Snapdragon 865, and it is continuing. We have even 888 and all of that. And here what we see is that the technologies that went into this MSMs over the period of time, starting with the 0.8 tech node to this 7 nanometer tech node and beyond. We have more cutting edge. So we have this 3D graphics, music, all the stereo headset, GPS, wireless LAN, video recorder, playback, then security, and the peripherals, then the fingerprint scanning, so many things. So those are all integrated. And we had this old bulkier phones to these latest generation phones that are there. Okay. Now we'll go through some of the other non-mobile, non-G technologies, like we discussed about this 3G, 4G, 5G. Now we'll see that how we have included other capabilities in our system on chip, that is also called the SoC. So our SoCs, starting with the 2000, year 2000, we started with the integrated audio capability. And these are even before the iPad era, these audio applications, we started enabling them in multiple ways with the software as well as the hardware that were present, and had the MP3 decoders, and initial MP3 decoders were available in the phones. And also we created that CMS, the compact multimedia extensions, having some of the time synchronized MIDI based music. And MIDI was one of the older standards, as well as other PNG graphics. That also was the graphical format, animation, also all of them. And we enabled the basic, very basic things like the ringtones, animation, greeting cards, and all that to start with era 2000. And it was quite well accepted by the customers because it enabled them to listen music. And we know in future there are other companies who really made a very big business out of it, and they were quite doing well because of the fundamental inventions that were taken up. We also enabled Bluetooth and GPS, and Bluetooth was such a successful protocol that it is even the annual device shipment we are expecting up to 6.2 billion at this particular time frame. And it is the low power wireless communication with at the peripheral level, and today we quite regularly use it in day in and day out, and that was also integrated and as part of the Qualcomm SoCs. And the GPS was quite important, and we will see later. I mean, there are some this called is I mean, Qualcomm also played very important role in terms of this GPS development. and later it became part of the Public Service Act 911 Act as part of which was passed in 1999. And what happened was we could able to use that mandatory requirement and also drive the Qualcomm based products because we were the pioneers in terms of supporting the GPS as part of our SOC that we had in 2000, starting from 2000. And 2002 onwards, after we are good with the audio and images, we thought of going to the next part, that is the video capabilities. And as you see, we had this QTV with the MPEG-4 and or H.263 decoders. It evolved into Q camcorder. It went into video phone and encoder, decoder, all of them were included. And we see that there were tremendous traction in this with the customer adoption. And more and more adoption it had, we could able to further reduce the price of some of these services, and that resulted in more adoption. And video was still the lot of technology development happened, including the video running on CPU, video running on DSP, and a lot of software stack, and many details that I think will not go into those details. But yeah, these are the significant development that the team took up. And all of them were done from scratch. And then came the similar way, the camera. So we thought that camera also is a important area, and because it's a mobile device and people are moving around, so they can identify some object and they can take the picture on the go, and always they don't need to carry the large, the bulky cameras, which otherwise also not power effective that way. And we thought of integrating camera because we, based on our analysis, and based on other technical developments, like we talked about the transistor packing capability that is there. So we decided that it will be good to include the camera features along with this video. And by the way, there is another aspect of the e-video that I mentioned, which was providing us more bandwidth. So we were sure that first of all, we are getting more bandwidth, so we can use that bandwidth for video communication as well as some of the camera applications. And also we are getting the advantage from the process side because of the techno transition. So we were addressing this requirement in a full-fledged way. So camera got integrated with the JPEG image, and then I think we'll not go into a lot of details, but integrated images, and then the lens related technologies, and all these things continued. Integration of camera, and basically it so happened that it became the mainstream. So some other camera companies, they had to finally recognize that mobile phone cameras are the mainstream ones. Then came to the graphics part, and the graphics is very important in terms of this other type of multimedia. Like everything is not video, but there are this automated generated content, or there are games and all these things which require the graphics to be visible and integrated as part of a smartphone. And also we'll see that how we had to increase the number of say processors, like there were workload in modem or there were workload in other processors. And similarly, we had to create our custom graphics processors to address the graphics requirement, and that also we did from scratch. Okay, so this is the graphics engine, the 2D, 3D graphics engines that came up, and we also had demonstrated it to the game developers and the gaming companies. They become very interested because like any other application, we found that gaming is also quite key, and a lot of users want to spend time, and that is their choice, and it improves the need for the these phones. as well as the data in certain cases if it is a distributed game. I mean, all the key areas in graphics like different transformations, lighting, shading, rasterizations of the triangles, and texturing, all of these, the algorithms were developed one by one. At some point of time, we had the partnership-based ones, but we also have the custom ones, which we developed from scratch. I think we have less time. Let us continue. So these are the examples of graphics. I'll not go into details, but it is also the again, like a compatibility wise, we developed this compatible OpenGL ES API based systems, which helped the different game companies to port their games easily through this OpenGL ES, and we build our graphic system which is compatible to this. And MSM 6550 was the one which had the OpenGL ES compatible graphics engine. I think we'll not go into any further details on this. This is also similar, covering the video capabilities, where it went, camera capabilities, what it was at that point of time, and MSM 6500 and 6550. So there were modem-wise no change, but this other multimedia and other SoC functionality was changed. So essentially, it is trying to say that how we kept our fundamentals the same, but improve other capabilities to ensure that customers are getting better and better features in their phones. These are some snaps from our original cameras. That is our MSM 6550. And these are all the high quality images at that point of time itself, and which got improved over the period of time. These are some of the phone demonstrations. It was quite sleek at that point of time, and then based on the 6550. And then there are additional phones, and as we see that we had many vendors around that time, Casio, Toshiba, LG, Samsung, all of them, and some of them continued in future. And the next slide is showing the integration. So I think we'll not go into this level of details, but net what we did was we integrated many things from platform to SoC. 2005, so what we did was we created a multi-CPU SoCs. That was MSM 7500, and multi-CPU means we had ARM CPU 11 for application subsystem and ARM CPU 9 for modem subsystems. And that is the time when we also were working with multiple mobile operating systems. That was the Symbian was there, J2Me, Palm OS, Windows Mobile, Brew, all of them, and some of them continue. It was pre-Android era, so there are history around this as well. But in summary, this multi-CPU was a major step because we could able to support more and more these features because of this multi-CPU decision. So our modem system also could able to scale up, as well as our application systems also could able to scale up. And this got in, through many changes over the period of time. But in MSM 7500, we went into this architecture. Let us go into the next one. So these are other phones, and these are even some of the tablet type of device that were envisioned, and some of the keypads went into as part of a screen. And we see the introduction of in the 2008-2009 introduction of Android. So Android came up around that point, and it was around Android 1.5 that was the initial cupcake version, and that time the previous one was a donut, and then the different HVGA displays were supported. Let us go to the next one. Will not look into a lot of details, but one thing is that we went into in 2007. It was a 1 GHz CPU, 600 MHz DSP, and we had also ATI GPU at that point of time, and then we scaled these ATI GPUs further, and and these are the state of the art at that point of time, and that got further this enhanced over the period of time. So Android versions also changed with the phones and integrated all the features, and we see the phones are becoming richer and richer. We will see that how our camera changed, like we are still seeing one camera, but then we'll see in future it become 2 cameras, 3 cameras, and many more. And those are all driven by customer requirements. And then our browser was another key part. So we worked with multiple browsers, like Nokia had browser, this Apple had have browser, Safari, and Android browser is there, Google, and few other browsers at that point of time. So we had the WebKit open source project support also was there as part of the browser support, because data means it is integrated with the web, and web means we have to access it through the browser. So the next step is this HD video, that is 1080p. We started supporting it from 8660 in 2009. Video playback, I think I'll just quickly go through. So it is 2009. Before that, it was 720p and all that, and we see the timelines over here, how it has evolved. Then 8660, still the evolution continues with the different Android versions, and around 2011 timeframe. And then we had the 4G LTE, and 2010-11 timeframe when we transitioned to the 4G era. So it was the MSM 8960 where this LTE multi-mode modems were there, and also we moved into 1.7 gigahertz guided CPU, multi-CPUs, and there are other sensor processors that came in. And on the cellular support, it was quite significant in terms of LTE, FDD, TDD, UMTS, CDMA, all of them. And why we need to support all of them? Because there can be the interoperability reasons in the worldwide way. Like there was an era when there used to be phones specific to Europe, phones specific to America, like that. But with our integration of the wireless technologies, we made it the whole core supporting all these key protocols, so that people can carry the same phone across the world without changing the handset. Let us go to the next one. Multiple sensor processors got integrated: accelerometer, gyroscope, compass, proximity, touch sensors, ambient light, all of them. And we had hardware as well as software-based mechanisms for the sensor fusion, and we could able to take many critical decisions based on different sensor fusion technologies to ensure that these action that are derived from the sensor are accurate. And then we had algorithms and the APIs, which are different software tools and applications. They took the benefit and build more and more features based on the fundamental capabilities that we had as part of the sensors and SoC integration. 2020, I think we'll not go into further details. We had 4K video cores, multiple GPU, quad CPU, and GPU had many additional features. And that was the era when we started with the 800 series of premium tier. So this is what is called the 800 series, and 800 series continued. In 2014, there are example of phones, and the recent Android versions like KitKat and all that got the support. Dual camera helped us in many things, like one camera was doing good at that point of time, but we found that we need to support additional features like the segmentation, background modification, refocusing, bokeh feature, instant autofocus, low light enhancement, many high dynamic range features, wide lens, and all this. So we thought that multiple cameras will be required for that, and we started with 2 cameras, and then we extended it into multiple cameras. And these are based on the hardware and the software. All these depth features, fusion features, zoom capability features, everything were developed. And going forward, this is a summary that how this 800 that we saw in the previous slide went into 820, 810, 820, 835, 845, 865, 855, 865, and 865 became this 5G capable with additional modem support, and these are the features that got incorporated, and these are different technology node how it transitioned. And the latest one, it is actually one of the latest. I think we have further down the line which are recently rolled out, but this is one of the latest, is the 888, which is in the 5 nanometer process. I'll not go into other details. These are net. It is a very significant advancement in terms of these capabilities, and it has taken the smartphone to a very long way in terms of advanced these capabilities and the features that users get. So these are the 865 based phones, and the key differentiator was the AI, and we will see some of the AI features going down. Okay, so the multi-camera also started coming in, and this megapixel support went very high. We are seeing 108 megapixel here in one of the Xiaomi Mi 10 Pro, and today's the latest ones are beyond this. And we are seeing similar multi-megapixel support not only in the backside camera but also the front-facing camera. One of the other important thing is that the video resolution improvement, which went from 1080p to 4K, and the latest ones are the 8K recording, and these are some of the examples. And we are seeing more and more 4K and the 8K content in say in internet, like in YouTube and all. We are seeing those this content coming in, and 4K itself is in a position to support 1 billion colors, and then 8K is much more than that. GPU, I think we'll not go into that. GPU and the graphics, basically, those are the game development, and we have the Xbox support and all that. So we are improving it continuously on the GPU performance. Mobile gaming is continuing because of GPUs and other processing units. So I'll not go into those details. That is quite improvement. And I'll just quickly touch upon this virtual reality, which we are supporting. Actually, it is called augmented reality, virtual reality, AR or VR. And in combination, we call it extended reality called XR. And that is the extended reality in practice we see in today in terms of the metaverse, which recently was announced by Meta, which was earlier known as Facebook. Then Oculus and Oculus Quest 2, and all of them with multiple different vendors. These developments continued, Microsoft and others, and it is still an active area where the focus is there to see that extended reality comes into mainstream, and it becomes as prominent as the mobile devices. I think, let us see. Yeah, one. I think this is one of the video that we have, but I think we are little running out of time. We will not continue with the video in detail, but this is a speech to text. It is a live speech to text. Maybe I'll just play it for a few minutes.
Another use case that I use personally a lot, and that is speech to text. On the two screens beside me, you can see that everything that I'm saying is being transcribed into English, and then it is further being transcribed into Chinese. And all of this is happening on the device.
Okay, so I think I'm not sure whether the video or the corresponding audio was available or not, but it was on-the-fly transcription from English to Chinese and vice versa. And that was a demo based on Qualcomm 888 processor by one of our senior vice president, and this is amazing. Like the way on device it does the voice transition, voice the recognition as well as transfer from one language to other language, transcode, that is really unbelievable. But it does it, and it does it quite well. And it is going to help the barrier across these languages, and we will be surely using it very actively in future, and a lot of benefit will come due to this. And we are seeing this similar transition, like if you go back from 1995 in terms of the process node and the feature. So we see that where it stands, and the features were quite limited, and it was MSM1, MSM2 era. And then in 2020, just if it is the 865 also, and the feature set and the benefits are quite high. And I think we don't have time to go into details. So this is where we have reached. And there are a lot of research going on, both in Qualcomm worldwide as well as in India, in many of the cutting edge technologies like artificial intelligence, machine learning, software related lot of research, compilers, and this fusion kind of a system like a hardware and the software together. And we see that there is tremendous potential, and the work that the India team and the overall worldwide team is doing is really cutting edge, and this is a really good experience that we are also creating, and we are driving it in our ecosystem, so that finally it reaches to everybody or most of the people, and we see a societal benefit based on the fundamental technologies and the products that we are developing. I think with this I will complete my talk, and maybe we can have some 5 minutes for question answer if any questions are there.
Yeah. Any questions from the audience? I have already seen one that probably you guys would like to get the slides. So don't worry, I have the slides with me, so that I'll anyhow share. But anything else other than that? Anything that you guys have in your mind? We have run out of time, but maybe if anyone wants to ask anything, we can probably take a couple of questions.
Please go ahead with the questions. Don't worry about the time. If you keep asking, I and Souvik will stay back. This is very important because though it seems like the presentations, you see how complicated the mobile devices become, which Souvik has tried to cover a couple of hours stuff in less than an hour. Yeah. So how it has become complex. There is so much engineering has gone behind, from VLSI to systems design to computer systems engineering to image processing to AI ML to DSP. So this we will be covering piece by piece. Not everything we can cover, but piece by piece in the upcoming talks. Please go ahead with the questions, and we'll be here to answer them.
Yeah. Any questions from the audience? So probably this was
makes processes faster, like from the conventional processors, the recent processors are much faster as we see. So what is the main reason behind that?
Okay. There are multiple reasons actually. See, I mean, when it becomes faster, there are many things to it. We have a frequency scaling, that is one part. Then there are multiple parallel execution engines, that is another way of looking at it. And there are many other architectural techniques. If you go through architecture books like Hennessy Patterson or something, you will see there are many techniques like speculative executions and all of that. So parallel processing capabilities and larger CPUs and many other advanced algorithm that goes in, as well as the frequency of operation. So everything matters, and everything is supported by the VLSI and the corresponding compilers and all of that. I mean, we set the target of benchmark performance for the new generation of processors, and based on that, we develop it and roll it out.
I think, Souvik, I just noticed today we are ideal combination sitting in this presentation. You covering the VLSI, I covering the software. Souvik is from VLSI background, I'm from the software background. Souvik talked about the VLSI magic which goes into the speeding up. Software is always slower in catching up with the hardware developments till now, but we are doing better. But in software part, like for let's say image processing, if you do tiling, you get a better cache performance. If you do loop unroll, there is a trade-off between the size of the code and speed, then vectorization, and so these things. So hardware plays a lot of role in speeding up the most of it, and software gets the last juice. Like your compiler guy will try to get more and more work done per cycle or per milliwatt. So it will be based on hardware and software combination. Hardware will do most of the horsepower work, and software will do again a little bit till the last juice we get. So compiler is one of the examples. It's Souvik already told.
Yeah, and just to be clear, guys, Qualcomm is working in both dimensions, okay? Because many people have this misconception that Qualcomm only works at the hardware level, you know. But as Sushim just pointed out, there's significant contribution from Qualcomm in the software dimension as well. So that is why this talk is kind of a mixture, a mixture knowledge dish, probably for multiple disciplines.
Yeah. Yeah, rest of the talks, we are mostly the software folks. So today is a very good chance where Souvik is from hardware background and I'm from software background. You can ask questions. Please go ahead.
Yeah, any other questions? So one of the major problem that we did not realize, we realized it only yesterday night, is that today was the last day for quizzes. This is the first quiz, so a lot of students actually like joined half, you know, whether in the between or they had to leave in between. So sorry for that scheduling problem. We are going to put up the talk probably, you know, as quickly as possible on the YouTube channel of IITISM. So that, you know, if you guys are planning to join us in the next iteration of this talk, you can anyhow go ahead and have a look at the talk even in the offline mode. So if there are no more questions, I'll just like to thank Sushim and Souvik. I hope.
Sure. Okay. No problem. I think thanks for the specific question, and it was really a pleasure to talk to IIT Dhanbad faculty and students. Thank you, Shaurav. Thank you, Sushim. And as we talked about Qualcomm, so if some of you join Qualcomm in future, then we can meet, and I think it will be a good thing to understand that a lot of engineering work is happening, and there's a lot of things to explore as part of Qualcomm.
Thank you, Souvik. Thank you, Sushim. Thank you.
One thing which missed from the Souvik's introduction is Souvik leads our Qualcomm's academic relations effort too.
Yeah, so basically he's the guy, guys, if you want to, you know, apply for interns, if you want to, you know, pick their brains, if you want to know more about Qualcomm, then Souvik is your guy. So I will probably, you know, share his email with you guys over email if required. So the YouTube channel is basically the YouTube channel of IITISM, okay, the official YouTube channel of IITISM. We will try to process this video as quickly as possible and put it there so that those students, as I said, right, sorry on my part for a poor scheduling. I did not know it was the last day for quizzes. So some of you had to leave in between and some of you joined us in between. So sorry for that. We will put the video on our YouTube channel. You can, of course, watch it during that, whatever time you get. Anyhow, so thank you, Sushim, thank you, Souvik, again, thank you, Abhishek sir, and everyone else who joined us today. I hope this session starts off, it kickstarts a long communication as well as a long collaboration between Qualcomm and IITISM. Thank you, everyone. Thank you for coming here.
Thank you.
Thank you.
Thank you.
Bye.
Thank you, Sushim. Thank you, Souvik.